Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to give more examples related to finding the coordinate of a vector with respect to a given basis. And here we have the coordinate vector px is given as 2 minus 3x plus 5x squared. So this is a polynomial of degree 2. And you are asked to find the coordinate vector of this with respect to the given basis. So here is the basis, and the vector space here is polynomial of degree 2. Now we can turn this information here and write it down in terms of the usual vector notation, which you have already seen in the previous video. Okay, so as an example here, let me just write it down straight away. When you have a polynomial of degree 2, it has the general form of a0 plus a1x plus a2x squared. So if you have this guy here, so we have three different vectors, not exactly in that particular notation, but here you can see that it's separated by comma. So we have three different components here for basis b, and then one here can be written in the usual vector notation that you are familiar with. So here is the position of one. Here is for constant, so here this is constant, this is x squared. So there is no x, 0, there is no x squared, 0. For this one, this is 0, 1, and 0. And for this one, the result here is going to be 0 for constant, 0 for x, 1 for x squared. And I hope you can see that when you combine these vectors together, it looks like RREF already. And this is the standard basis, actually. Okay, this is the standard basis. Standard basis, due to the fact that you have values of 1 at the first component, the rest are all zeros for the first one here. For the second one here, you have 1 at the second position, the rest are all zeros. And similarly for this one, you have 1 at the third position, the rest are all zeros. So this is a very specific basis, special case of basis. We call it the standard basis. And we have already seen in the video that when you are dealing with the standard basis, the coordinate vector can be obtained straight away because you can just read it from the given vector. So this is the given polynomial of degree 2 here, which you can turn into the usual vector notation as this one, and it will look like this: 2, negative 3, and 5. And so you can think of it as vector v, if you like, similar to what you have seen in the previous video. And the whole thing here is basis. Okay, therefore the starting point to find the coordinate vector is, of course, to combine basis and this vector together. Yeah, so the starting point will be to write down 1, 0, 0, 0, 1, 0, 0, 0, 1, and here is 2, negative 3, and 5. And as you can see, this is already in RREF. You don't have to do any operations anymore. Therefore, the answer can be obtained straight away. So here is the answer for coordinate vector for px with respect to basis is given by 2, negative 3, and 5. Right, so this is the answer. Now, here's a quick question related to this example. So what if the basis given here is changed so that it looks like this, so that it looks like x squared, x, and 1. So when the position of these components here are changed or switched, well, you have to remember that when you get 2 here, 2 is related to the original component. Here we have 1. So negative 3 is related to x here, and 5 is related to x squared. Therefore, when the basis is changed to this arrangement, the coordinate vector for px with respect to this basis, we have a slightly different basis now, is going to be switched. You can see that for x squared, we're going to have 5. X is at negative 3 still. 1 here will be, the answer is 2. So that is the short explanation, where you can see that, well, you just switch the position of the values given here as well. Now, what is the long explanation? Well, the long explanation is like this. So long explanation. You can see that in this case, basis is different. It is given as x squared, x, and 1. So if you consider vectors here, it will be, for this one, 0, 0, 1. This is 0, 1, 0. And this is 1, 0, 0. Therefore, the combination of all the vectors in the basis is going to look like this. And here we have, what is it here? 2, negative 3, 5, okay? So here is 2, negative 3, and 5. And clearly you can see that this is not RREF yet, so you need to do the operation. You can see you have to switch. So this is okay. You have to switch the first row with the third row. So when you switch the first row and the third row, you will have 1, 0, 0, 5, 0, 1, 0, negative 3, 0, 0, 1, 2. Therefore, now since we have RREF, excuse me, therefore the coordinate vector for this with respect to basis given here is 5, negative 3, and 2. And what I'm trying to what I'm trying to stress, the important point here is that the order of vectors in basis is important. You have to follow the order, and based on that you should adjust the coordinate should the order of the basis here is changed. Okay, next is find the coordinate vector for this matrix here, A, with respect to B. B is given by the combination of all these four items here, and it says that they are all standard bases of matrix 2 by 2. So this is a matrix 2 by 2. Now, what it means when you say it's standard basis? It means that for this one here, you will have at the position 1, 1, you will have 1, 0, 0, 0. Everything else is 0. Here, you will have 1 and 1, 2. First row, second column, so 0, 1, 0, 0. This is 0, 0, 1, 0. And finally, this one is 0, 0, 0, 1. So this is the combination of all matrices here. We'll make it as a standard basis for matrix 2 by 2. Now, what we can do is we can again turn this into the usual vector notation that you are familiar with. We're going to write it down in terms of, for example, here, what we have is, okay, let me just do this. So here what we can do is we can turn these values so that it looks like this. So this one can be written in terms of 1, 0, 0, 0. So we go this way, 1, 0, 0, 0. 1 0 0 0 for this one. For this one here, the second E12, it will be 0 1, so 0 1, and then 0 0. This is 0 0 1 0, so I hope you can see the order. And here is 0 0, which is here, 0 1. And you can clearly see that the combination of all these four matrices here in this manner will give you RREF already, and you should get RREF because you're talking or you're dealing with the standard basis. And for this part here, this can be turned into, again, you go like this, so 2 negative 1. So you go by rows, okay, so 2 negative 1 and then 4 and 3. Okay, so that's the first, or that's the starting point. And based on that, we can see that this is already RREF. Therefore, you can clearly read from this part here. So that would be the coordinate vector of A with respect to B is just 2 negative 1 4 and 3. And that is what you need to know. Whenever you're dealing with the standard basis, you will get the answer for coordinate vector will be the vector given in the question itself. Okay, right. Now here is another example, but this is going to be a bit long because here the basis is not standard. The basis is defined as such, and you are asked to find the coordinate vector of px here with respect to basis C. So as always, what is P2? Polynomial of degree 2, which has this general look of A0, A1x, A2x squared. And I'm just going to write this one here in terms of the usual notation that you are familiar with. This would be, well, this is constant 1, x is 1, x squared is 0. And we are done. For this guy here, constant 0, x1, x squared 1. And finally, for this one here, constant is 1, x0, x squared is 1. Okay, so that is C. And for this one here, vector, we can write it down in terms of, we can think of it as, you know, the vector px. So we have 1, 2, negative 1. This is a vector of inside that particular subspace. Now, to find what is the coordinate vector, we need to combine this, the basis, and this one together. So we're going to consider the augmented matrix of this value. So 1 1 0 0 1 1 1 0 1, and right next to it is this vector 1 2 negative 1. Okay. Now what I can do is, well, maybe I want to switch the second row with the third row. So switch R2 with R3, and it looks like this one 0 1 1 0 1 1 negative 1 1 1 0 2. Next is, I would like to change this value to be 0. Therefore, R3 plus negative 1 R1. So 1 0 1 1 0 1 1 negative 1. So 1 minus 1 0, 1 plus 0 is 1, 0 minus 1 negative 1, 2 minus 1 is 1. Okay, right. Next is I'm going to turn this value into 0. Therefore, R3 plus negative 1 R2 will give me this result. 0, 1, 1, negative 1. So 0 plus 0, 0. 1 minus 1, 0. Negative 1, negative 1, negative 2. 1 plus 1 is 2. Next is turn this into 1. So multiply the third row with negative 1 over 2. And so the result is 1, 0, 1, 1, 0, 1, 1, negative 1, 0, 0, 1, negative 1. Okay, now what I can do next is, well, I should turn this to be 0. So to be 0, that means I will have to consider the change is in R1. So R1 plus negative 1 R3. So 1 plus 0 is 1. 0 plus 0 is 0. 1 minus 1, 0. 1 plus 1. 1, negative 1, negative 1. So 1 plus 1 is 2. So I change that to 0. Next is I can change this value also to be 0. So that will be considering this process R2 plus negative 1 R3. 0 plus 0, 0. 1 plus 0, 1. 1 minus 1, 0. Negative 1 plus 1 is going to be 0. 0, 0, 1, negative 1. So here I have arrived at RREF matrix, and based on that I can see, let me just erase this part. Well, based on that, since this is already RREF, therefore the part right next to it here is the coordinate vector. So it is the coordinate vector for Px here with respect to C. C is the basis, and the answer is 2, 0, negative 1. There you go. Alright, here's a little bit of theorem before we end this video here. Now, based on this theorem, it says that we have basis given as a combination of all these vectors, and then we have u and v to be vectors in that space. Let C be a scalar. So therefore, how can you find this the answer to this question? What is the coordinate vector for u plus v with respect to basis b? Now remember what we have done so far is, well, what we have done so far is we have basis and we have vector v. So based on this, we combine b and v together. We do the elementary row operation, and we turn b into RREF, and what we have here is going to be coordinate vector for v with respect to b. So this is what we are looking to find. We're looking to find the coordinate vector of v with respect to b. Okay, so that's what we have. Now imagine the theorem here says that what if you have not just one vector, but you actually have two vectors. you actually have u vector as well. So based on this, how can you find the coordinate vector of u plus v with respect to b? Now, it explains here that what you have to do is essentially you can apply the same process, but you do them separately. So here you get vector u, try to find what is the coordinate vector of this. Okay, so you do the usual process as what I have explained previously in this video. You do that process in order to find the coordinate vector for vector u. So the process is the same as explained here. And then you do the same process again, so you repeat the process, but this one is to find the coordinate vector of v. So once you get the result, you can just add the two results together and you'll be able to answer this question. So basically that's what the theorem says. Also, if you have a scalar c and you are asked to find what is the coordinate vector of c, c is a scalar, vector u with respect to b, and in order to find that, you can just consider taking out c. So here c is a constant scalar, c, and then you just go on and find this guy here. So you just need to find what is this coordinate vector of u, and again the process is the same thing as what you have seen previously in this video. So as simple as that. Okay, now there's also another interesting theorem here. Well, what we have here is we have b as a basis for vector space v. So here is combination of vectors, and then we don't have one vector, we don't have two vectors. Here we have one and two vectors. Now we have a lot of vectors, and to represent a lot of vectors, we just use the same notation with, the difference is in the subscript here. So we have a lot of vectors now, u1, u2 up to uk, and it says here that u1, u2, uk is linearly independent if and only if you can find the coordinate vector for u1, coordinate vector for uk, and the result of all these coordinate vectors is linearly independent. So that's a story. Okay, well, how can we draw this ideal? Basically, here we have some subspace. So we have vector space. Okay, let me just write down here. We have vector space. So for this vector space, we have you can have b. B is given as the combination of all these vectors. Okay, and then here we have many vectors. We can have vector u, vector u2, u1, u2, and uk. And we have seen previously that we can link these vectors with a basis. And since we have many vectors, therefore we can think about u1 as the combination of c1 v1 plus c2 v2 plus ck vk. So this is just for u1. Of course, for u2, c1 v1 plus c2 v2 blah 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 ck vk. And we have many vectors, so up to the last vector here. Okay, and how do we get this c1, c2, and ck? Well, the process have already been explained process is such that you combine all the bases together. This one is the vector. You do ERO, elementary row operations, and so it becomes RREF, and here you will get, I'm running out of space, let me just write down in terms of vertical process here. So ERO, so you will get this becomes RREF, and you will be able to get coordinate vector for U, UI with respect to basis. Okay, so the results that you get here, this is the result that you get here, this one actually. So you want to get these results here. These are the coordinate vector of U. How can you know that they are linearly independent? Well, they are linearly independent if the combination of them 0. So linearly independent is when you combine all the vectors. So C1 plus C2 plus dot dot dot. This is equal to 0. And based on that, so this is the starting point, C1, C2, and so on must be equal to 0 as well. So that is the definition of linearly independent. So it says here that the vectors given in this vector space, which means this one, so here is U1, U2, UK. You want to know if it is linearly independent or not, you have to go and check the coordinate vector for each U1, UK and see if the combination of them here is linearly independent. If the coordinate vectors here are linearly independent, we can say that these vectors here are also linearly independent. So it implies this one-way street. So check this one, is it linearly independent? If it is, then these vectors here are also linearly independent. I hope I have managed to explain it clearly to you guys, but if you have any question, do let me know, and thank you very much for watching this video.